Well, thanks for having me. It's exciting to be able to kick off the DataEDGE conference. As Anno said, I spoke at the very first one. And when I spoke there 4 years ago, I think the AMPLab was just getting started. And so I talked about my best guess at what we were going to be doing. 4 years later, it turns out we've done a lot. And so I kind of want to bring you up to speed on what's been going on at the AMPLab, what we've been researching, what we've been building. And then, as Anna said, we're going to turn it over to Ali Godsi, who's going to show you the Databricks platform, which is a hosted analytics platform built for data scientists in a startup that basically spun out of the AMPLab. So we'll talk about some research stuff and about some of the commercialization. So why don't we get started? So I'll go very quickly and say a little bit about big data, defining it. I will not present the 3 V's. If anyone wants to know what the 3 V's are, you can talk amongst yourselves. Somebody will tell you. But let's just, sort of for level setting. So here's one of the world's worst definitions of big data. And it basically says that, it's if you have some amount of data that's, so big that it's hard to work with. And this is a problematic definition for a couple of reasons. One is just sort of trying to operationalize it. What's it say? So if you have billions or trillions of records, it's big data. So what that means is if I have 1 billion minus 1 records, it's not big data. That doesn't really make sense. The other problem with this definition, the reason I don't like it, and this, by the way, is a definition that you'll get if you look online. The other problem with it is it describes data as a problem, right? I've got so much data, it's just so hard to work with. It's a problem. And that misses, as far as I'm concerned, sort of the promise and the excitement about doing data analytics and working in this new age of big data. So I don't have a crisp definition yet, but I do like this quote that came out in one of the O'Reilly pamphlets on big data, in particular, a pamphlet about using big data for healthcare. And the basic thrust of this quote is that, for a long time we thought, this treatment was roughly 80% effective for breast cancer patients, but now we know much more. We know that it's 100% effective in 70 to 80% of the cases and completely ineffective in the rest, okay? And this sounds, if you think about it, it may be a little flip, but it's actually quite a deep insight. And it really gets to the heart of what I think is important and interesting about this whole new world of big data, which is if you can collect enough information about enough different instances of whatever it is you're trying to study, in this case patients and their outcomes, at sufficient granularity, you could start to see things that you couldn't see if you didn't have access to that data, right? So there's some sort of a phase transition where you've collected enough detailed information where all of a sudden you can start to see things that you couldn't see before. To me, that starts to get a more positive and a more useful definition of big data because it speaks to the promise and to the things that we can do with data as we're able to collect more and more of it. And in this case, if you think about it, if you could come up with a drug that maybe only cured some small percentage of the people who have some horrible disease, but you can figure out exactly who that's going to cure, that's actually a huge breakthrough. And it's going to mean a lot to those people. So, this is what I like to think about heading towards a definition of big data. Now, the place that we saw this in our work in AMPLab, it's sort of what drove it home to me is, when we started the project, we're sitting at the university, we're trying to get our hands on real data, and we decided that one of the things we'd do to get data would be to build some apps and see if we could generate data on ourselves, by ourselves. And so there's an app written called Carrot that basically runs on your smartphone, watches what applications you're running, watches what's happening to your battery, and then uses that information to tell you how to manage your battery better. And it just so happens we released the app. It got written up in TechCrunch and a few places like that, and it went viral. And so, what it looks like is here. You've got your smartphones. Periodically, each phone will report up to our application that's running in the cloud. And then our application basically collects all this information and it builds models. And it builds models about, for a particular phone, running a particular version of an operating system, how do certain applications use the battery, right? The applications that you're running, what happens to your phone, to your battery when you're running those applications? Now, that's not very useful data on its own. But if you're lucky enough, and you can get written up in the right places, you can go viral, or at least viral for an academic project. We've had, I think at this point we're probably close to 1 million downloads of this application. And now, once you've got 1 million people that are running this thing, and all those 1 million phones are reporting this data up to the cloud, then you have the opportunity to aggregate that data, and then build real useful models about, for given phones, which applications are correlated with heavy battery drain. Okay, those we call hogs. And then, more importantly, or maybe more interestingly, you can also look for an individual phone. You can see what's going on that's anomalous, right? And then what that lets us do then is to give very detailed reports back to every user saying, hey, if you seem to be running a particular application a lot, and that application is a known battery hog on your phone, and if you stopped running it, we predict your battery would last an extra hour and 47 minutes a day. Well, how do we know that? Well, we've seen enough people that have a similar profile to you who aren't running that application, and we know how long their battery lasts. Okay. Likewise, we can also say, hey, whenever you run Google Maps, your battery drains really quickly, but other people that have your phone don't have that problem, right? So maybe you should uninstall it and reinstall it. Maybe there's something going on with your setup. So again, this sort of gets to the heart of what's interesting about big data and big data analytics, which is if you can collect enough information at the proper level of detail and granularity, you can start to see these patterns, and then you can use those patterns to give people or companies or whoever you're working with actionable information. Okay? And if you don't have enough of that data, you won't be able to give any useful information. Okay, so it's that same definition. Okay, so that's all I want to say about defining big data, but a lot of the talks I give, especially in front of academic audiences, there's so much hype around this term big data and data science and these other terms that I tend to, there's some natural indication, especially amongst academics, to kind of push back. And so, the point I want to make is that whether you agree with the argument I just made or not, I hope you do, but whether you do or not, one thing that's for sure is if you've been working in this industry for a long time, and I have, and I know a number of you have, the underlying technology has changed fundamentally, in the last 10 years. It's a completely different world in terms of big data technology than it was, in the era before big data. And so, just a couple things to keep in mind about what's changed. First of all, just the ability to scale. Just add more and more processing. If you get more data, you add more and more storage, and the system can just expand and grow. Okay? This has always been a goal, but it's been a hard goal to achieve. Now it's just sort of standard. Everyone expects it. More importantly, you don't have to provision and buy, or buy and provision, a huge set of resources, right? In the old days, you had to think about what was the biggest possible application you were going to build, or the largest your company was possibly going to get. And then you would have to try to, scrounge up the money to deploy, the data center or whatever that you were going to build your data management system on. Put that all into place and then get it up and running. And now you don't have to do that, right? Because of things like public cloud computing, you can just pay incrementally, right? So you can start small, you can grow big. If you grow to a certain point and then you don't need all that capacity, you can shrink back down, right? So you get elasticity. This is fundamentally different than the way it used to be years ago. Another thing for data management that's really important is this idea of flexible schema management. So one of the buzzwords out there these days is a data lake. In my research, we used to call this a data space. But the idea is in the old days, you would figure out what exactly every piece of information you're going to collect looks like, how it's related to every other piece of information you're going to collect. You would map that all out. You'd code that up in, say, a database system, and then you could actually start collecting data and do something with it. And now that's been completely reversed. Now you just collect the data, you store it in the scalable storage, and then you impose the structure on it when you need to, as you need to. Okay, so this has fundamentally changed things. If you look at the newer platforms, and Ali is going to show the one that's based on Spark, it used to be that you had stovepipe systems. If you wanted to do database query processing, you would run on a relational database system. If you wanted to do graph processing, you would get a graph system. If you wanted to do text processing, you would get a text system to do that. Now, this stuff's getting much better integrated. And so it's easier to sort of start with a bunch of data and then use whatever modality or combination of modalities that you want to process the data. So that's changed. Lots of different languages that you can use. And then the one that I'm going to focus the rest of my time on is that by and large in the big data space, the innovation is happening in the open source. Okay, so in the old days, you know, there were a handful of big companies that were basically building the innovative products, and you had to wait and see what they would come up with. Nowadays, it's grassroots. People are building systems and putting them out in the world for people to try, and there's this whole ecosystem being built. And there's a constant change, constant generation of new technologies. And this has fundamentally changed. So even if you don't like the term big data, and I know I'm sort of talking to a friendly audience because you wouldn't be here if you didn't like the term big data, but even if you don't like the term big data, you got to admit things are completely different. Okay, so if you're working in the data management world, this world is very different than what it looked like 10 years ago. And that to me is really exciting. Okay. So I was hoping Anna would say it, but she didn't. The Berkeley Data Analytics Stack is abbreviated BDAS, and it's pronounced? BDAS. BDAS, thank you. So we're going to talk about BDAS. Okay, so where did, first we'll talk about a little bit about where it came from. So, you know, we have this thing up the hill called the Berkeley AMPLab, and what it is, it's a collaboration of a bunch of faculty, and all told about 80 students and postdocs and researchers that are focused on building tools and algorithms and such for dealing with big data. And what's interesting about this particular group of people is we come from sort of a wide swath of at least the computer science landscape. So I won't say that we incorporate everybody, but in most computer science departments, you know, there's a group that does machine learning, there's a group that does systems, there's maybe a group that does database systems, and they're in different parts of the building, they often don't talk to each other, and we set out to break those walls down. So we put together this group of people, we built a big open space, and we had, you know, we encouraged people to all sit together and work together and talk together. And what we've got now after all these years is really a community of people who can kind of move across all those different areas. So if you meet a student from the AMPLab, you might have to talk to them for a while to figure out if their concentration is in machine learning or in systems or in data management, because they're very fluid moving across those boundaries, and they don't really even see them as boundaries anymore. And so that's been a huge, you know, if I look at success that we've had since I was here 4 years ago, that's one of the big successes I think we've been able to pull off. Now, the name AMP is an acronym for Algorithms, Machines, and People. And the idea is that those are the three resources that we want to figure out how to put together to make sense of big data, right? So algorithms, you know, think about machine learning and statistical processing. The machines part, we're thinking about cluster computing and cloud computing. And the people part, when we started, I have to admit, we were thinking mostly about crowdsourcing and human computation and sort of human-in-the-loop processing. But we've realized over the years that, well, you know, you also have to be thinking about the data scientist that's sitting at the other side of all this processing, and that's what Ali is going to show in his demo, how that's evolved over time. Okay, so that's the AMPLab, Algorithms, Machines, and People. Another thing I'll just mention briefly is it's a really interesting combination of a public-private collaboration. And so our funding, for those of you in academic world who care about such things, is about half and half from the White House Big Data Initiative that they announced in 2012, and the other half comes from all these companies. And so we get to have really good engagement with, as you can see, many of the leading companies in data management and in web systems and social systems. So it's another unique aspect of the AMPLab that we get to cross, you know, sort of the traditional research boundaries and, you know, the more commercial side of the world. A big part of what we do, and the reason I think we've had a lot of uptake of the software that we've been building, is that we put a lot of effort into building community. So really leveraging the fact that all the action in big data is happening in the open source world. And so here are some events that we run. We started with a meetup group in San Francisco probably 3 or 4 years ago. I took the screenshot yesterday. There's currently 62 Spark meetup groups around the world in 22 countries, almost 20,000 members. And so this thing has really just taken off. I mean, this is a bunch of graduate student software that we're talking about, at least it used to be. And we run different meetings and meetups. Okay, so great. So that's a little bit about the background. So now let me talk more about BDAS and what it is. So all of this started, I think it's fair to say, when a bunch of people at companies like Google and Amazon and Yahoo and you know, sort of big web companies and cloud companies realized that they were going to have to be processing volumes of data that were beyond what most places had ever had to deal with. And if you looked at sort of the existing commercial products, whether they were relational databases or other types of systems, either those systems weren't going to be able to scale to the loads that these people needed to process, or even if they would scale, they were going to be crazy expensive and kind of inflexible because the software was all hidden, you know, it's all proprietary software. So companies like Google and Amazon started building their own infrastructure. In particular, Google was very successful at building scalable data management systems for their own internal use. And they were very careful not to let those things out. They eventually started publishing some papers about them, but for years people were using these very scalable data management systems that weren't available anywhere else, and that's still going on. I mean, they're still, you know, pushing the frontier of a lot of this stuff. One of the most popular things they did was something called Mapreduce, which was a fairly easy to use system that would allow you to write a program once and then have it run on parallel systems of any of sort of arbitrary size. So it let you, you know, specify your computation in a way that it could be easily, you know, split into pieces and spread across, you know, the machines of a cluster, whatever size you needed. So eventually the word about Mapreduce got out. There was a group, I think, I don't know whether they started at Yahoo, but a lot of the work was at Yahoo. But there's a group that said, hey, you know, I used to work at Google, and I really miss this MapReduce thing. So what I'm going to do is I'm going to build a version of that, and let's do it in the open source. And so there was a system called Hadoop that was born, and Hadoop contained two parts. It still does contain those parts. You know, this MapReduce processing engine and a very scalable file system. This was the introduction, the first introduction that a lot of people got to parallel processing at scale. And a lot of people got really excited about it. But what happened is they said, well, you know, MapReduce is pretty cool, except it doesn't really do exactly what I want, right? Because what I want to do is I want to process graphs, right? I got graph data, I got to process that. Or I want to run SQL queries, right? And I can't really do that well on MapReduce. Or I want to do real-time processing, and MapReduce is more of a batch system. And what happened was, all these different groups of people out there started specializing the MapReduce. And take MapReduce and say, okay, I like MapReduce, but I'm going to change it to do this other thing. And you end up with this explosion of all these different systems that don't really talk to each other, okay? And this process is still going on. Now, if you're trying to deploy a real-world data management infrastructure, this is wonderful because you have all these different systems that are available, and most of them are available for free download. But the problem is, you know, they don't talk to each other. They're changing constantly. You can't tell which ones are ready and which ones aren't ready. And it's a real management nightmare, okay? So it's great that there's been all this innovation, but in reality, it's kind of hard to manage. So what we did in AMPLab is we said, okay, well, we like MapReduce too. But what we're going to do is, instead of specializing it for every different thing we want to do, let's try to expand it. Let's try to grow MapReduce, add some functionality to it so that it can do more, okay? And as it turns out, there are basically two additions that you need to, that we added, let's say, to do MapReduce to enable all those different modalities. And they're basically the following things. The first one is, you need to be a little more general than map and reduce, right? That's too limited a language. So you want to be able to allow a much more flexible computational model. Okay, and so we allow programs to be general directed acyclic graphs, so they don't have to be just mapped and reduced and mapped and reduced. Okay, that's the first thing. You make the language more general. And then the second thing is, for performance, you want to make sure you can share data across those different operations that you're doing. And I'll show you what that means in a second. But take my word for it, that if you do those two things, then you can implement SQL, you can implement a streaming system, you can implement a graph system, you can implement a lot of your favorite machine learning algorithms, okay, on on top of the same platform. So now you don't have, this huge, zoo of different systems that were never meant to work together. These things all work together. And also, if you have a bunch of data and you want to treat it as a table and run SQL on it, you can do that. Or if you want to run your favorite machine learning algorithm on it, you could do that. And you don't have to copy the data from one system to another. Okay, and remember, the word big really does mean something. And if you have to copy your big data from one system to the next, every time you want to do something else with it, it starts to get hard to manage. So if you can keep everything in the same system, you don't have to copy things around so much. Okay? So that was the insight. And just to show you what we mean by generalizing MapReduce, here's what some of the operators you can do in Spark. You can do map, you can do reduce, and then you can do a bunch of these other things. And if you're a database person, this should warm your heart. There's joins and group bys and other things. But there's a bunch of other operations here too that if you like doing machine learning and so on, that are going to be useful. Okay, so that's what Spark does, is it expands the language that MapReduce provides. Okay, so on top of Spark, what we're doing, so that gets us to what BDAS is. So BDAS is really a top to bottom stack of a bunch of open source software that we've been building using the system Spark that I'm going to tell you about briefly as sort of the middle of it. And so it's kind of good to read this thing bottom up. Each blue box is a system that we've built in the AMPLab. And you can generally think of each box as being 1 or 2 PhD theses. That's kind of how it's turned out. Amazingly, right? The gray stuff are just other things that we depend on pretty heavily that we didn't do. But if you read it from bottom up, there's a bunch of resource virtualization stuff. We built a system called Mesos. It actually started in the project before AMPLab. But there's a company you might have heard called Mesosphere that's now handling Mesos. It's an open source project. And interestingly, Apple just gave a talk where they don't usually say stuff like this, but they announced that Siri, maybe not on purpose, but that Siri was running on a cluster of some number of thousands of machines that was managed by Mesos. So, so this stuff is out in the world being used. We have a storage level where we use the Hadoop storage system pretty aggressively, as well as other storage systems. But we've built on top of that a caching layer. It's currently called Tachyon. You might have seen that there was a company spun out about that recently. And then Succinct is a compression layer that sits on top of that. So Tachyon's a caching layer. Succinct is a compression layer. Spark is our engine that I'll tell you about. And then all this stuff up here are just different ways of getting at the data. So there's a streaming interface, there's Spark Streaming. There's a graph interface called GraphX. There's a whole stack for doing machine learning. There's a whole stack for doing different types of relational query processing, including approximate processing. And then there's some stuff that we're expanding the stack for doing more real-time machine learning. That's what Velox is. And that's the BDAS stack. So what do I want to say about it? Oh, I'll also mention there's a bunch of applications on top of it that we've been building too. So what I want to do, I want to make sure there's enough time for Ali to show you the current instantiation of a lot of this stuff. So I'm going to spend just a couple minutes giving you a little background on Spark, and then I'll try to wrap up shortly after that and turn it over to Ali, and then there'll be time for questions after. Okay, so let's talk about Spark. So Spark is a system. It was actually started around the same time the planning for the AMPLab started. The main student behind it is a guy named Matej Zaharia, who just this year won the ACM Dissertation Award. So ACM is the main computer science research organization. They give an award to the single best dissertation of the year across computer science across the whole world. Matej won that. Another student in our lab, John Ducci, who's a machine learning expert, actually was one of the 2 runners-up for that award. So, and they only let you nominate 2 people, otherwise we probably would have won them all. That's my guess. Okay, but anyway, so that's Spark. Matej now is a professor at MIT. We don't like to talk about that, but and John is a professor at Stanford. We don't like to talk about that even less. Okay, but we developed it in the AMPLab. It's an alternative to Hadoop MapReduce. And as I showed you, it's kind of what sits in the middle of the stack. And it's now an Apache project. So as students graduate, their code tends to graduate with them. And so Spark kind of moved into the greater world. And if you ever hear of Apache Spark, that's what it is. That's what it turned into. Okay, giving you just some interesting quotes that people have been saying about it. Okay, so if you were to go to the Apache Spark site and download Spark, you would get Spark, but you would also get all this other stuff too. You'd get parts of machine learning library, you'd get the SQL system, you'd get the graph system streaming, and an interface from the statistical language R. So that's what Spark looks like when you download it. We're heavily leveraging open source, so even though our lab has maybe 40 people who do programming on a regular basis, in the last release of Spark, there were over 400 contributors, right? So you get to leverage all these people around the world who like doing open source code. If you compare it to other popular open source projects, it's been more active in the past year than just about anything else. So that's an indication that it's grown beyond the walls of our lab. And kind of the key insight behind Spark, there were two, as I mentioned. One is this thing that I already showed you, which is you want to expand the language, so not just map and reduce, but map and reduce and join and filter and all these other things. The second thing, though, was about sharing data across all those different operations, and this is why Spark runs fast. So here's what happened. If you looked at Hadoop MapReduce, and let's say you wanted to train a machine learning model. So you'd start off with some initial model, you'd have your training data. What you'd do is you'd read it into the machines of your cluster from disk. You would apply these map operations. So map basically takes an individual record as input and outputs an individual record that you might have transformed in some way. And then you collect those through a phase called reduce that's running on different machines potentially, right? So you do shuffling across the network. Then you do a reduce. So that's where the name MapReduce comes from. Those are the two things you could do. Map applies to individual tuples. Reduce collects them and does aggregations and combines them in various ways. When you're done doing your map and your reduce, stuff gets written back out to disk in Hadoop. That's how it works. Okay, and you get your new model. Okay, great. But the problem with a lot of machine learning algorithms is you're not done yet. You want to iterate, right? You want to, exactly. You want to keep running. You want to keep improving your model, right? And so what do you do if you're trying to do this in Hadoop MapReduce is, well, okay, I read in my training data again, maybe to the same machines, maybe not. I map it again, I reduce it again, I write it out to disk again, and I get another weight vector, and I keep going, and I just keep doing this. So if you look at what's happening here from a systems point of view, every iteration of that machine learning algorithm, you're reading stuff in from disk, right? Yeah, okay, and then you're writing it out to disk, right? And then, right. And so, you know, if you think about it, what's happening is each iteration of your algorithm is communicating to the next one through the disk, which is about the slowest possible way you can communicate in a computer system. Okay, it's one less mechanical device in a computing system, and that's what you're using to communicate. So what Spark does instead is say, okay, well, what I'll do is I'll read data into memory, and then I'll serve it out of memory, okay? And then I'll allow each of these different iterations to access data that the previous iteration wrote in memory. Okay, so I'm not communicating to the disk anymore, okay? And that gets you, a 10 or 100x speed up over generic Hadoop MapReduce. Okay, now the idea behind this is that Mate defined the notion of an RDD, or a resilient distributed data set, which is basically a collection of data that's spread across the cluster. And the cool thing about, well, an interesting factoid about RDDs is that they're immutable. Okay, it means you can't change them. Okay, so you create an RDD. The only thing you can do with an RDD is apply an operation to it and create a brand new RDD. Okay, and the way you do computation is by applying, these operations and creating a sequence of RDDs. It turns out, though, that model, right, of having this limited language, but bigger than map and reduce, and applying them to immutable objects, to these immutable collections, is sufficient enough to handle all those different types of interacting with the data. So you can do SQL processing, you can do graph processing, you do iterative machine learning, all in this model. And that was kind of the big breakthrough of what Mate came up with, was he sort of came up with the minimal model, the minimal set of things you need to do to handle a bunch of things that people want to be able to do with big data. Okay, that was kind of the beautiful part of Spark. And then, of course, a really nice implementation of it. And so what this lets you do, and I'll go quickly here, but what this lets you do is, you might be asking yourself, okay, well, these people that did Hadoop were not dummies. So why, I kind of make this cheap joke about communicating to the disk. But why did they do that? Was it because they didn't know that memory was faster than disks? No, of course they knew that. The problem is that they were designing for a very hostile environment. They were designing for an environment where you had thousands of machines possibly, and those thousands of machines were not very well taken care of. And if you were running any sort of a big calculation, chances are that during the middle of that processing, one or more of those machines was going to die. And if you didn't build your system in a way that it could recover from those individual small failures, you would never make any progress, right? Because you'd have to start all over again, and then when you started the next time, something else would die. And so the reason Hadoop uses disk so much is because at every step you're writing things out so that if anything fails, you can go back, grab it off the disk, and continue processing for the part that you lost. Okay? So it's beautiful. It makes perfect sense. But it turns out that if you're willing to buy into this model that Mate came up with of these immutable collections, you could do something simpler. That basically, this is an operation in Spark where you're saying you're reading a text file, then you're applying this filter to that text file, so you're just pulling out the lines that contain the string error, and then you're going to pull out some of the columns, some of the fields from those lines that contain the word error, okay? And you store that in an RDD called messages. What you can do then is during runtime, you can store this as basically a recipe. So if I ever lose any part of my message RDD, right? So the message RDD is spread across the cluster. If I ever lose any part of it, I can recover it with this recipe, okay? I read in the appropriate blocks from HDFS, I apply this filter to it, and then I apply this map function that pulls out the right columns, okay? And that's all the information you need to be able to read, and where the pieces are, which I'm not showing here. If you have that information, you can recover any piece, okay? So the fact that RDDs are immutable is what gives you this flexibility. If you could go in and change any little piece of an RDD at any time, this bookkeeping would become much more cumbersome. But because you can't change an RDD, it's very simple to keep track of the recipe of creating any RDD. And it was that sort of combination of features that led to Spark being able to do all the things that people wanted to do, but to be much faster than Hadoop MapReduce. And that's largely why it took off. Okay, so let me, I'm going to not say much about Spark SQL, but there's a new, so that's Spark. And I showed you what Spark looks like. It's, you write in Scala or in Python or something else. A lot of people like to write in other languages like SQL. So Spark SQL gives you a really nice way to do that, and I think Ali is going to show a few things about Spark SQL. But what's nice about it is it lives in the Spark environment. So if you have an application you want to write that involves some hairy machine learning libraries that you like to use, and involves some hand-coded Scala processing you want to do, and uses some SQL for doing query processing, you can put it all together, okay, in a nice, seamless way. So hopefully we'll see a little bit of that in the demo, but that's Spark SQL. And if you go to get Spark, as I mentioned, the current version of Spark is 1.3, and it includes all that stuff I showed you, the streaming interface, the graph interface, and so on. And it has these different interfaces, so you can access it through Java or Python or R or these different ways here. And what's interesting about Spark now is it's available in all the major Hadoop distributions. So for a long time, before it was Apache, the AMPLab was doing the Spark distributions, but we don't do that anymore. And now it's companies like Cloudera and Hortonworks and MapR and IBM and people like that that are distributing it. Which also makes it easier for people to use because they're not dependent on any one vendor anymore. So that's cool. So let me just, I think I want to wrap up and then turn things over to Ali. But let me just sort of give you the bigger picture. So, I mentioned that as students graduate, the software tends to graduate with them. So if you think of that stack diagram I showed you where we had virtualization on the bottom, storage, and so on, basically, the lower parts of that stack are pretty much done from a research point of view. Those students have mostly graduated. And what we're doing in the AMPLab now is moving up the stack. And so a lot of what we're doing is looking at how do you support different types of analytics applications. So how do you look at, how do you support, in particular, genomics or Internet of Things types of applications? Or things like the phone application that I showed you. How do you support those efficiently? And what we've come up with is we want to leverage all those nice things about big data technology that I told you about, right? The scalability, the pay-as-you-go, the ability to have flexible, schemas. But you want to be able to do this in an environment that you have some control over. And so what we realized is that if we can give people a way to define their data model, right, just the way you would in a database system, but using modern technologies where it's not all or nothing, right? In a database system, when you define what all your data is supposed to look like, it either fits or it doesn't, right? And if you try to insert something into the database that doesn't conform to your schema, the system throws an error, right? That's not the way these systems work. And so we wanted to figure out how do we get the benefits of understanding what the data looks like, but also being able to leverage the flexibility of schema on read or some of these other flexible techniques. And so what we've done, especially for the applications, is we said, okay, let's start by defining a data model using modern technology. So we tend to use something called Avro, which is a way of describing, it's an open source system for describing data. There's a bunch of interesting formats that people have come up with. There's one we use a lot called Parquet, which takes the data, stores it in columns, allows you to do certain types of compression. And so, try to use these kind of emerging standard techniques and let people define the data. Once they do that, then you can do the things you're used to doing in database systems. You can change the implementation below that data model, and you can change the implementation of the applications and the analytics on top. And this is the thing that a lot of people had missed, right? People that were trying to do data analytics but hadn't come from a traditional database background didn't really understand, I think, the importance of having this data model in the center. So we do that, and what that lets us do then is we're starting to move towards an environment where, just like in a relational database system, where when you want to ask a query, you sort of say what you want that query to do, but not necessarily how to do it, right? And the system then compiles that statement through the schema into the implementation. We're trying to do the same thing for machine learning. Okay, that's really where the lab is going. And so we're building a system called MLBase, where you say at a very high level, I want to do clustering, I want to build a recommendation system. There's a handful of things you can do. I want to predict this value based on this other data. And then the system will take that high-level statement and translate it into the right algorithms and operators, how those things are related together and where they run on the cluster. A lot of the processing you want to do has a bunch of knobs you need to turn, so we try to set those knobs automatically. And then, a big part of any learning process is figuring out what features matter. And so we're trying to automate a bunch of that. So, where the lab is going from this base of building, this very scalable, flexible execution engine is this way. You define your schema, you use this scalable execution engine to implement things, and then you say at a high level what you want to do, and we try to do the translation automatically. Okay. And obviously we're going to leverage all the stuff that we've built. All right, so with that, I think I want to make sure Ali has time to show you the demo. I think, why don't you come up, Ali? And then hopefully there'll be a little time for questions about this stuff after. So I'll turn it over to Ali.
Thanks, Mike. So I'm Ali, and I'm one of the co-founders of Databricks. So I have a presentation and I have a little demo in the middle. So the presentation sort of is more, Databricks has these, talks that we usually give to companies, but I actually changed it here. What I'm going to do instead is I'm going to give you a little bit like the history, because we're all from Berkeley. And, all this basically started with the work that was done at AMPLab. So Mike overviewed, the research that they were doing all these years. But really, I was there at the same time, and there were two things that really stood out. I mean, two things that really made these projects really successful that I think differed from many other research projects that I saw. One was that it was really cutting-edge research that they were doing. PIs like Mike and other professors, they were working interdisciplinary. So actually Spark, the first time I got into the lab, it was some guy who wanted to do machine learning. He's actually now a professor at Stanford. And he wanted to, participate in the Netflix competition, and he didn't care about the kind of stuff that we were doing on systems. He just wanted to solve the machine learning problem. So that's actually how Spark started. It was Matei, this grad student, helping him figure out how to do this kind of machine learning really fast. And MapReduce wasn't cutting it for him because between each iteration it was really slow. So they were doing all this interdisciplinary research. They were working with another project here, Mobile Millennium, that was using taxis and tracking where people going in cars. So it was cutting edge research, and as you heard, Matej actually recently just got the ACM Best Doctoral Dissertation Award, which is the most prestigious award you can get for your PhD thesis. So that was one thing. But another thing that was actually maybe more interesting, that without it, it would have been impossible to be this successful, is that people like Matej and the people that were working on this project were spending something like 50 to 70% of their time just fostering the community. They were participating in mailing lists, answering people's questions, helping them get this stuff set up, traveling around in the Bay Area, going to companies, giving them tutorials, hands-on, configuring it for them and so on. So this was much of the legwork or groundwork that actually led to this community growing, and becoming what Mike was saying. And what they basically built was this thing that you see here. I don't know if I can. This is Spark. This is an illustration of what Spark looks like. The really nice thing about it is that at its core, it has these RDDs that Mike explained. The RDDs are actually what's Matej's PhD thesis. That's the one that got the award just recently. What that does is it basically gives you a way to describe a collection of objects. The objects can be anything. They can be records, whatever you want, but it knows how to parallelize and distribute them and recover if a machine is not there. Okay? This differed greatly from what other people were doing, because at that time, if you wanted to do something more advanced, if you wanted to do streaming, so if you had live real-time data coming in, you would have to use one system. So there's a system out there, Storm. Or if you wanted to do machine learning, there were other systems that people were building just for that. There's whole companies like GraphLab that just focus on that. Or if you wanted to do graphical computation, so you have a social network, you want to recommend friends, you would use another one. So what Spark really did is unify all of these, so you could use all of them with one abstraction. So that was really the strength of it. And people could then throw away all these lines of code that they had to otherwise write and just use one system, reuse their own code, and avoid all this brittle transferring between the different systems. So that was Spark in a nutshell. So we started Databricks taking this stuff from AMPLab, and we wanted to commercialize it. And this was in the summer of 2013. And really our goal was really simple. We just wanted to make big data simple. Really all you want to do is you want to get insights from your data. Insights is just a fancy word for statistics. So you just want to extract some statistic from lots of data that you have. Now, if I give you 1 million data points and I tell you, here's 1 million integers, get me the average number. It's really easy. You just paste it into Excel, you click average, and you get the average out immediately, really fast. Anyone can do that, right? It's so simple. If I give you the same task and I tell you, here's a petabyte of numbers, integers, give me the average. Now it's rocket science. Okay, you need PhDs, you need to set up clusters. It's really complicated, right? You need lots of different tools. So this was really why we wanted to do Databricks. We were thinking, it shouldn't be this. This is crazy. It shouldn't be this hard. And we really firmly think it's not going to be this hard. 10 years from now, petabyte of numbers is going to be as easy as 1 million numbers. It's just that computing research isn't there yet. We haven't really done all the research and built the systems needed to abstract away from one single machine. Shouldn't matter if your data is on one machine or 100 machines. That should just be abstracted away. So that was Databricks' initial goal. And really, it was based on 2 bets. The 2 bets were, one was that we thought that Apache Spark had a good chance to becoming the de facto engine. So it had those ingredients to unify these different things you wanted to do in a really simple manner. We thought we could maybe make it replace the existing clunky tools that were out there, like MapReduce. So that was number one. And the second thing is, we thought that to go all the way, to really make it simple, there's a lot of operations involved in getting 100 machines and setting them up and all that. So the second bet, or the second insight